Morning, everyone. My name is Desmond, and I'm here with Shreya, Gabe, and AD, and we're members of the campus space and energy management team of Code Plus. I'm going to start a little bit about our motivation. As we all know, it's been Duke's climate commitment to reduce its carbon emissions by 50% by the end of 2030 and beyond. As such, we've been tasked by Duke Facilities, Jeff and Greg, who happen to be our stakeholders, to create a predictive occupancy model that allows them to track occupancy within certain spaces so they could be able to adjust heating, water, and lighting systems. As we also know, building occupancies throughout the day and the year fluctuate, and this leads to energy costs, CO2 emissions, and poor space utilization. We believe with our tool, we will be able to build a robust model that predicts occupancy well in order to cut costs and effectively utilize space. Now, a bit about project goal. As I mentioned earlier, is to create predictive occupancy models. And the way we're doing this is by using Wi-Fi data, where we check the connection logs that happen throughout the entire day and use it to predict occupancy. To supplement this, we'll use changes in CO2 concentration levels within rooms to do this as well. Now, I'm going to hand over to AD to talk a little bit about tech stack.
Thank you, Desmond. So as Desmond mentioned, we are using Wi-Fi connection logs. It's over access points over campus and a CO2 sensor, Atlas IoT, put in our Raspberry Pi. And the Wi-Fi logs are being sent to a database. It's a PostgreSQL. And the Raspberry Pi is sending over the CO2 sensor data to a Linux web server and in a fast API endpoint. All of this is going to a data repository, which in the next slide, we are also counting the physical count of people in each room to make a sustainable data repository. And with that, we are making our regression models, which is a product, and we are using Python with Jupyter for the backend and voila widgets for our front end. And that's how we create our interactive dashboard. And now I'm gonna hand over to Desmond to talk about the Pi.
Thank you, AD. So right now, AD and I are going to spend the beginning of our time talking about CO2 side of things, while she and Gabe will talk about the Wi-Fi side of things. For the CO2, as I mentioned earlier, we're using Atlas Scientific CO2 sensor, as you can see on the right-hand side, and this is connected to a USB board and to a Pi casing as well. And on the left-hand side, we have a Raspberry Pi unit, and this together collects live collections of CO2 together with the timestamps and the room locations. Now, the way the sensor works, on the right-hand side, we have an inlet that allows CO2 molecules to enter the sensor and an outlet that allows CO2 molecules to exit. Now, when the CO2 molecules enter, there's an infrared light source that is shown through. The molecules absorb some of this light source, and the rest is what is detected by the active sensor, and it's what we see as concentration in parts per million. Now, the accuracy of our sensor is about plus or minus 5%, which is about 50 parts per million, and it can detect concentration ranges between 10 and 10,000 parts per million. Now, the infrared light source generates a lot of heating and temperature at the beginning, so we let it sit for about 5 to 10 minutes, and then after that, we use every data to make our models. Now, I'm going to hand over to AD to talk about CO2 methodology.
Thank you, Desmond. So our methodology is mainly using two working Raspberry Pis. Both of them are placed in the same room. We are placing them in different locations to test the factors in CO2 and air are well mixed. And the results we have this readings from both Pis in the same day in the same room. And the left one, you can see it ranges up to 1100. The second one ranges up to 700, but they have the same decreasing line flow. This can be because of the location, perhaps the ventilation, the AC positioning, if the doors are open or closed, but maybe further research is needed. And our data collection for that, as I said, is in a Linux virtual machine. We are storing this Raspberry Pi data in dictionaries. In the left image, you can see we have a sample reading. It's just the number of CO2 in parts per million. But in the next slide, we saw that could be improved. So we improved that to add the timestamp, the room it's being collected. In the right side, it's the endpoint in the API sending that data. And now Desmond's gonna talk more about how we're exploring it.
Thank you. So we did a little bit of exploration with the CO2 data that we had, and we decided to do an average CO2 concentration against number of occupants. So what we did was we collected CO2 concentration within the room every at 30 seconds interval, and we tracked occupancy as well. So when there were zero people in the room, we averaged all those CO2 values, and then we did that for the rest of the occupants as well. And as you can see on the left graph, the maximum average CO2 is about 1,060, while on the right-hand side, the maximum is about 620. And this is due to the disparities AD was talking about. And for Pi 1, we had an R squared value of about 0.78, while for Pi 2, we had an R squared value of 0.95. This is quite high, and we believe that we need more data to be able to make sure that it's more robust. And so we went ahead to do a little bit of models as well, and we took into account the volume of the room. So now we have the volume, we have the area given to us as GeoJSON files, and then we just multiply by the height of the room to give us the volume. And what we did was we created distributions for the CO2 as well. So when there was zero people, we averaged the CO2 at a specific time from both sides, and we averaged that over that time interval. And this created ranges of CO2. And as you can see, that as occupancy increases, the average CO2 per volume also increases as well. And on the right-hand side is a way of also seeing the left-hand side graph, but it's in the form of heat maps. So on the right y-axis, we have average CO2 per volume as well, while on the x-axis, we have the hour of the day. And then on the left y-axis, we have the time interval, 15 minutes interval. Now, we want you facilities to be able to see the time as it goes. And so from 10 to about 2, you could see that those buildings are heavily occupied, while from 3 p.m. onwards, there's not many people there. Now we're done with the CO2 side of things. I'm going to pass over to Shia to talk about why.
Thank you. So now Gabe and I are going to talk more about our second variable, which is Wi-Fi. And the way we're tracking this is by using access points, or APs. And these basically just allow us to connect devices to wireless networks. Here on the left, you can see a picture of an access point in Bostock. And on the right is an image of all of the access points and their locations in Bostock Library. So to use these, we've been taking the access point data from a large Wi-Fi database called Splunk. And here's an example of some of that raw Wi-Fi data we've collected. We get a bunch of different variables, such as timestamp, the access point name, the net ID of the person who logged into the Wi-Fi, along with the SSID or the Wi-Fi they logged into, whether they reassociated or authenticated with an access point, along with their hardware ID or MAC address. So all of the data we've used over these 10 weeks ranges from June 11th to July 3rd. And a really important thing to mention is that all of the data, the net ID and the MAC addresses have been SHA encrypted to preserve privacy. So to use this data, we've been storing it inside of a database called PostgreSQL. Here on the left, you could see an image of how we've been using SQL queries to create new table spaces in the database. So we could copy all of that Wi-Fi CSV data into Postgres for further analysis. And so Gabe's going to talk about some of that analysis.
Thank you, Shreya. So over about the span of a 3-week time period, my teammates and I, we frequently walked around the Bostock building and just counted the amount of people in the building at that time. And that's what you can see here in red. And on the same graph, what we have plotted is just the number of unique users every hour during the same time period. And what we noticed is there seems to be a pretty strong correlation between these two variables. And what we wanted to do first was see how strong the relationship was between the amount of people counted and the amount of variables. And second, we wanted to see how much variability we could describe using our models. So to answer the first question, we started with some basic linear regression models. The first one that looked the most promising was the unique users, and we received an R-squared value of 0.82. But somewhat surprisingly, the strongest correlation happened to be just with the total number of entries, which is just a 40-minute window from when we observed the data, and we received an R-squared value of 0.89. And given this information, we wanted to further our models and make it as strong as possible. So we developed a multilinear regression model that incorporates the previous two variables, as well as the MAC address and also the day of the week using one-hot encoding. And we received our strongest R-squared value yet of 0.93. Now, given all of this information, we plotted the observed counts next to the linear regression prediction using that multivariable linear regression model. And as you can see from this, you can see how accurate our model was at predicting how many people were in the space at that time, as you can see based on this graph here as well. Now, moving on, we want to show you a little demo of our website and what it currently looks like right now. As you can see, we just have a nice little homepage here that shows who we are. We have our mission page, which has the Duke climate commitment, our goals of decreasing energy and CO2 emissions, and space optimization. We also have the About page, which shows you what data we're using, which is Wi-Fi and CO2, and also just a little bit about the team. And then finally, we have our most important page, which is our track occupancy page. This has all of our dashboards, the first one being our heat map, which we built. And this just displays a heat map of the Bostock building. And it has all of the access points as little semicircles, which you can click on to get a better reading of where people are at that specific time. We've got our Wi-Fi graph, which has the starting date and ending date. You can put the interval as well. And you get this graph that just depicts how many people are in the building. And then we have the data, which you can also download if you want to do that as well. And finally, we have our CO2 graphs, where you just choose the specific room number and the time, and it displays a map of the amount of people using the volume and CO2. And then it also displays a heat map of the CO2 in parts per million. Now I'm going to pass it back to Shreya to talk more about some of the limitations of our project.
So if we're only using CO2 and Wi-Fi data, we've seen some limitations. As for CO2, there are a few confounding variables. Ventilation indoors might be inconsistent throughout the day, and outdoor weather conditions could also cause fluctuating CO2 levels. But the most important limitation was our hardware limitations. Fortunately, we only had 2 Raspberry Pis to use, so it made it hard to do really large-scale, large room CO2 analysis. As for Wi-Fi, the main issue here is that all of the logs are centered around access points. So it's difficult to do more specific room by room analysis with just Wi-Fi. There could be background noise because people have multiple devices, or people outdoors might connect to an indoor AP. And finally, there's no Wi-Fi signal strength in the logs. But if this project were to continue in the future, here are some supplemental data sources that could help with that, such as humidity, temperature, and Bluetooth. And Desmond's going to talk about more of our future steps.
Thank you, Shreya. Looking ahead into the future, we believe anyone carrying on this project should refine the front-end UI UX so it becomes very easy for our stakeholders to be able to use our models as accurate as possible. In addition, we believe that more data needs to be pulled in order to improve our model. And finally, to be able to update our application in production. We currently have the development and main branch side of things, and we hope to always update that and always push to production. So it's always updated. And to summarize this whole presentation, one of the main things we learned from this is that CO2 sense allocation matters, and it has ADA in the disparities, and we believe that there's a lot more research that needs to be done. Secondly, there's a strong correlation from the Wi-Fi data points, as it's a strong indicator to predict occupancy. And finally, to be able to produce as robust models for Duke facilities as possible, so they could be able to accurately predict occupancy. And finally, we'd like to thank our stakeholders, Jeff and Greg, for this exciting project. My teammates and I are really learning a lot from it. And also like to thank our team leads, Mark and John, for their immense technical expertise in making this project happen. And we'd like to thank Code Plus admins, Isabel and Jen, for making this 10-week project a reality. And thank you for giving us your time today.